Welcome again to Engineers Newsletter Live. When we read your reviews and suggestions following each Engineers Newsletter Live program, it's clear that you want more chilled water system programs. Now, we also know that you can't always attend a program, which is why we make them available online for continuing education credits. For those of you craving deep dives, here's a list of past E&L programs that focused on chilled water systems. As you can see, we've covered topics on variable speed drives on compressors and everything you ever wanted to know about coils, even chilled water terminal systems. In 2013, it was all about variable speed chilled water plants with a focus on the heat rejection side of the system. In 2011, it was upgrading existing chilled water plants and ways to improve what you already have. In 2008, small chilled water systems. Now, as we travel the country and the world talking to you, quite often we get requests for abbreviated takeaways from the most popular programs. So, today we bring you a program that provides some new information as well as highlights from some of our more recent chilled water related programs. A blend of old news, and new ways to consider old topics. And whenever possible, we'll also give you data backing what we see as the trends in chilled water system design. To cover the information today, we have a guest, Mike Patterson, who is the product manager for Trane centrifugal chillers. And you're likely familiar with Susanna Hansen. Susanna is a Trane applications engineer with expertise in chilled water systems. Together, they will share what we are experiencing out in the field. So Mike, can you get us started with the prime mover in the chilled water system, the chillers?
Thanks, Jeannie. To begin today, we want to spend some time covering the bigger trends in chiller design we are seeing throughout the industry. Now, this isn't everything, but we felt this will be the most meaningful to you. In short, we want to provide you a sense of where we are today with chiller design and where things are headed in the future. We will first focus on centrifugal trends and look at air-cooled trends later on. First, we will look at design trends that affect the chiller itself and wrap up the section with where the industry is headed with regards to controls. This is perhaps the area where we will see the greatest advancements in chiller plant design. As we demand more and more from our chiller plants, the need to control them precisely becomes more critical. As you will see, the demand for more efficient designs is one trend that is not going away. Understanding equipment design trends will help you better understand what equipment is currently capable of and what advancements you may see in the future. Topping our list of equipment trends, we will first look at the industry's continued march towards greater efficiency. Now, I imagine this is not a shock to anyone, and we will talk more about this in a minute. The next trend we will consider is the continued growth of variable frequency drives throughout our industry and its impact on chiller plant design. We will look at how they impact efficiency requirements and ultimately how their use impacts design. Over the course of the last 15 years, our industry has seen new compressor designs across all chiller types. We will take a brief look at what is driving these designs and what factors will drive future trends. Another trend we will touch on is the growing customization of equipment to meet application-specific requirements. The first two trends influence this one and have resulted in some unique methods for saving energy, driven by what the application offers. Think heat recovery, for example. And finally, we want to spend some time better understanding the rapidly changing global regulations around refrigerant. This is perhaps the most immediate of the trends. So, let's first dive into our continued march towards greater efficiency. Many of us are familiar with ASHRAE Standard 90.1 and the work it has done to improve the energy efficiency of our buildings. Tables 6.8.1 detail the minimum efficiency requirements for HVAC equipment to include chillers. Now, my intent is not to report on minimum efficiencies, but instead to take a more holistic view of energy efficiency in order to show where we have been and where we are going as an industry. By showing the improvement in the minimum efficiencies over time, I hope to better illustrate this. As many are aware, federal regulations and DOE have been steadily pushing for lower and lower energy use over the past decade for a multitude of reasons. We are not going to take time and investigate these reasons, but it is important to note these actions do not look to slow down. For example, ASHRAE 90.1 is currently evaluating over 20 proposed addenda that will influence future energy codes and regulations. So, with that in mind, let's look at how energy efficiency requirements have evolved over time and where we are headed. This diagram was created with net zero energy use at the bottom and progress towards that goal indicated on the right-hand side. In short, energy regulations are driving towards net zero. The basis of a 100-site EUI was set by the status of the commercial building stock at the turn of the century. As you will see, the 90.1 standard has made significant progress over the years. The 2004 standard cut energy to just below the 75-site EUI value, and the 2010 version took it down to the halfway point. 2013 brought us even closer to the net zero goal, but we still have a ways to go. The importance of efficiency in equipment design is not going away. In fact, the other trends we will discuss all contribute to making the chiller and system around it more efficient. So, with efficiency continuing to be a hot topic and one that we do not see going away anytime soon, what can equipment manufacturers do to continue to meet the ever-increasing stringency of energy regulations? Well, variable speed drives, when employed correctly, have provided a means to better take advantage of conditions that offer energy-saving opportunities. In the case of centrifugal chillers, that opportunity arises when ambient temperatures allow for condenser relief. Many have and continue to incorporate VFDs in chiller design, and their use is common. However, 20 years ago, it was a much different story. This graph represents the trend of centrifugal VFD use since 1995. As the price of VFDs has declined, their use has increased. However, it was not until around 2005 we saw a rapid increase in their use. Throughout the years, chiller plant designers have gained a better understanding of how best to employ VFDs in their designs to capture the most savings. For greater detail on how to employ VFDs throughout the chiller plant, reference the E&L broadcast from 2013 and earlier this year that dealt explicitly with this topic. Now, what do we expect to see in the future? There are two possible scenarios here. Let's look at the first. One possible scenario is continued growth towards 100%. Now, hitting the 100% mark seems unlikely when you consider VFDs are not advantageous in all applications. For example, climates that offer little ambient relief, areas with high demand rates, multiple chiller plants, high or even sometimes medium voltage applications, and others that do not provide situations that would leverage VFD benefits. That is where scenario 2 comes in. Considering the situations mentioned above, we could arguably see a scenario where growth begins to taper off, plateau, or even shrink. As engineers better understand how and when to employ VFDs effectively, it becomes apparent that not all applications warrant their use and provide the owner's required return on investment. The E&Ls I mentioned above will help to better understand when and when not to utilize VFDs. So now the question is, can we get any more out of variable frequency drives as they relate to chiller plant design? Or have we achieved all that's possible? Have the efficiency standards squeezed out all the savings? Well, the answer is, there is more out there. Here's a historic graphic that shows the increase in ASHRAE 90.1 minimum chiller efficiency in terms of coefficient of performance, or COP. The two lines represent full load COP at AHRI standard conditions and the integrated part load value, or IPLV. Now, as a reminder, IPLV was first required by 90.1 1999, so until that time it is not plotted. You probably already noticed the split in 2010, introducing Path A and Path B. We see that minimum chiller full load efficiency flattens out between 2010 and 2013. but there are more efficient chillers that can be selected. The dots represent data from premium efficiency chillers. In other words, ones selected for very high full load performance and others selected to achieve a high IPLV. So what does this all tell us? Simply put, there remains additional chiller efficiency levels to design into chiller plants. In fact, over 20% higher full load and 25% higher part load efficiency. Earlier this year, we had an E&L detailing how to take greater advantage of drives. I would suggest reviewing it to learn more about what actions you can take in your designs to leverage greater efficiency. Outside the inclusion of VFDs on chillers, we have seen the introduction of new bearing types, resulting in new compressor designs over the past 15 years. These new designs have allowed for higher speeds, giving compressor designers additional options to meet requirements and providing greater opportunities for VFDs by taking advantage of opportunities to lower speed when ambient conditions allow. Now, I will not spend time on the advantages and disadvantages of this, but want to touch on what it means for us today and for the future of chiller design. To begin to understand how compressor design and speed impact overall design, let's take a look at the specific speed formula, or what is the most efficient speed to spin at? To answer this question, we need to look at three significant components. Lift, which speaks to the size of the impellers. Tons, which speaks to the volumetric flow through the compressor. And refrigerant choice, which determines volumetric flow and is a significant determiner of efficiency. These three items drive the design's specific speed, or more simply put, the optimum speed to spin the impeller in order to achieve the best efficiency from that impeller. This more readily translates into RPM. Now, please recognize this formula has been simplified to illustrate the correlation between these variables and how they relate to the speed of the impeller. Let's take this a step further and look at how this would apply to a chiller. Now, you'll see that RPM is on the y-axis and tonnage on the x-axis. As you decrease in tonnage, RPM needs to increase to drive towards the design's specific speed. With speed determined, subsequent design decisions can now be made, one of which is bearing choice. As you see on the slide, the greater the speed, the fewer bearing choices you have. Rolling element bearings typically are found in applications operating at speeds less than 25,000 RPM. Air and foil bearings stretch to around 45,000 RPM, and magnetic bearings can go much higher. With speed as an output, it can limit a designer's choice of bearings. Now, of course, manufacturability and cost are also key factors in the ultimate bearing choice. The graph also illustrates the impact refrigerant choice has on specific speed and ultimately bearing choice. To achieve optimum specific speed, low-pressure refrigerant designs yield lower operational speeds than do medium-pressure designs. This results in more bearing choices for the compressor designers. The takeaway here is that lift, tons, and refrigerant choice are three primary inputs towards ultimately determining a compressor's efficiency. There are other inputs, but these are critical in that determination. Speed is simply an output that then drives bearing choice. If you want to significantly affect compressor efficiency, adjust lift parameters, tonnage, and select an efficient refrigerant. Now, let's turn our attention to applications and how they drive chiller plant design. We are seeing chillers being asked to do more than just comfort cooling. More and more designers are looking for more efficient ways to design building HVAC systems. They are utilizing heat recovery, ice storage, cold water storage, free cooling, and other application-driven enhancements to increase the efficiency of chiller plants in the overall building HVAC system. Over the past decade, we have seen an increase in the number of manufacturers who offer these enhanced application chillers. Whether it is air-cooled or water-cooled, these enhancements are no longer considered niche offerings. Advancements in controls and packaging techniques make seemingly complex solutions common. As efficiency standards continue to become more stringent, HVAC system design will demand these types of application-driven enhancements to find the energy savings demanded by local regulations. Now, let's take a look at a recent example of how heat recovery was used to make the building design more efficient. Susanna will tell us more about how an ice arena in Quebec leveraged both the heating and cooling aspects of the chiller to find an efficient solution to their unique application.
Ice arenas obviously require special operating conditions to ensure the rink is at optimal conditions. What may not be so obvious are the other aspects of the arena that require comfort cooling as well as heating. Traditional ice rink systems use ammonia or CO2 systems and require specially trained technicians to perform service work. So the challenge was to find a solution that could satisfy the 10-degree temperatures required by the ice, plus the more traditional comfort cooling temperatures, as well as provide water temperatures up to 115 degrees to preheat domestic hot water, heat the snow melt system, and reheat the dehumidification unit, all while providing an easy-to-maintain and highly efficient system. Sounds easy, right? Well, it really was. Employing a 250-ton RTWD chiller, along with a dry cooler, the arena was able to meet all the requirements, providing excellent ice conditions and a comfortable environment for spectators. Now, many of us may not have the opportunity to design an ice rink, but this example illustrates the wide range of applications that cataloged products are being asked to handle. And we expect to see this trend continue.
One of the things Susanna mentioned in the previous example was the use of ammonia and CO2 as refrigerant. As I mentioned in the introduction, the topic of refrigerant is arguably the most immediate trend to pay attention to as we continue to experience ever-increasing pressure on global refrigerant regulations. Discussions around global warming potential, natural refrigerants, flammability, and efficiency are common topics in the world of refrigerant. Although we do not have time to discuss all of these, I do want to highlight some things that will help you navigate this latest trend. With the recent proliferation of low GWP alternatives offered by the chemical companies, countries have been moving rapidly to take advantage of these new refrigerants. In the United States, the current administration has developed a climate action plan that targets HFC reduction, among other actions, and the Environmental Protection Agency has adopted new regulations through the Significant New Alternative Program, or SNAP, to institute these goals. For example, a proposed rule change by the EPA would delist R507A and R404A as acceptable refrigerants for new and retrofit retail food refrigeration beginning in 2016. Likewise, R134A would also be delisted under the same proposed rule for new standalone retail food refrigeration and new vending machines. Although these are recent actions, the pressure on HFCs is not new and has been building for well over a decade. Now, looking across the pond, the European Union passed a law that took effect January 1st of this year to phase down HFCs by 2030. This move aligns with efforts by several nations at the Montreal Protocol to institute a global phase down of HFCs. Most notable of these is an amendment by the North America contingent led by the US, Canada, and Mexico. More recent was an amendment put forth by India calling for the same. Now, if you tie this together with China's recent commitments to reduce emissions, it is generally believed that a global agreement on HFCs will be achieved within the next 1 to 2 years.
So Mike, let me make sure I understand the significance of what you just said. It sounds like the refrigerants we use today are not the ones we'll be using tomorrow. In addition, the shift to next-generation refrigerants is happening quickly, as evidenced by the building consensus for a global HFC phase-down. I would imagine we'll start to see manufacturers begin introducing products with next-generation refrigerants to stay ahead of this shift away from HFC refrigerants.
Exactly. In fact, we are beginning to see this. For example, Trane has introduced 2 new chillers with next-generation refrigerants. An air-cooled chiller with R513A, which is a R134A replacement, and a centrifugal chiller with R1233ZDE, which is a replacement for R123. Now, I know that was a lot of information in a short amount of time, but we wanted to provide you with some general trends that will continue to affect equipment. Now, let's look at another set of trends within the world of controls. It is controls that will ultimately determine the success of a design. If the right controls aren't in place, then the system will not operate as intended. The three trends to pay attention to: the continued move to and demand for open protocols, greater connectivity of controls between unit, system, building, and enterprise controls, and lastly, the growth in diagnostic tools offering users greater insight into the health of their chiller plant and overall HVAC system. Over the past decade, the industry has seen a shift from proprietary protocols to open protocols, such as BACnet and Modbus. This trend continues and has fostered the other two trends we will look at in a moment. Opening protocols provides customers greater choice in controls, challenging manufacturers to differentiate through capabilities. In a Frost & Sullivan analysis, BACnet made up almost 40% of the BAS protocol market, while proprietary protocols shrank to less than 28% of that total market. As the protocol field becomes less congested, the new challenge becomes greater connectivity. With the various levels of control becoming more sophisticated, for example, unit level and system level controllers, the need to connect more and more equipment together has become greater. As wireless technology continues to improve and become more integrated into everyday life, we are seeing it make its way into our industry in the form of wireless thermostats and on some unit controllers, for example, VAV boxes. In the case of chiller plants, wireless controls could appear on sensors, pumps, and valves. The benefit being ease of installation and lower install costs, no wires. Now, expect this trend to continue and see it employed on more and more equipment to make it easier to connect the building. As we gain better connectivity throughout the building, this will result in greater amounts of data to analyze. Understanding how the system operates under real-world conditions opens the door for operators to make adjustments on the fly to fine-tune and ensure efficient operation. However, in order for them to better analyze the data, diagnostic tools will need to become more sophisticated and provide not just information, but also analytics that help operators make changes in operating parameters or look for preventative maintenance opportunities. Expect to see more dashboards customized to specific customers to offer these types of analytics along with remote monitoring services to help aid in troubleshooting and preventative maintenance. One example today of this is intelligent services from Trane. Think OnStar for HVAC. So how would this work? Let's consider Bullitt County Public Schools in Kentucky. Using intelligent services, they were able to monitor, analyze, and act on not only system alarms, but also monitor energy usage throughout the district. In addition, the remote monitoring features allowed maintainers the ability to check temperatures, set points, and alarms from a single dashboard page on the web to review the information. With IS Active Monitoring, technicians were dispatched to answer critical alarms. This type of diagnostic capability is becoming more and more popular, providing building operators greater analytics to catch issues earlier and to continuously optimize their system to ensure they are achieving peak efficiency.
With all those chiller and chiller control trends already occurring, you may be asking, how are we doing, theoretically anyway, in our typical design practices for chiller plants? If you turn the crank on an energy model, the minimally compliant water-cooled chiller plant, just meeting 90.1 2013 requirements and using good design practice for decisions where there are no requirements, leads to a chiller plant that will be quite good in annualized energy consumption, in kilowatt hours per ton hours. In reality, though, there is no certain answer to how well the typical new chiller plant actually operates today, even if it does meet code. Our models show that it's possible to be excellent, that is, below 0.7 annualized kW per ton, while only just meeting the code minimum requirements today, using constant speed chillers and a fixed tower set point. As Mike showed, significant improvement beyond the minimum code for chillers is available, both for full load and part load. But the vast majority of difference between high and standard performance chiller plants is earned in their design and control, in the ways that chiller plants, intentionally or not, deviate from the energy models. So that's what we'll be discussing next. It's important to watch chiller trends because how we design the chillers affects how we control the systems. We have to constantly reevaluate what we know about how to do things. VFDs on components has been the core of no less than 5 of our last programs. Some of them, like the one earlier this year, went really deep. So we thought we would zoom out a little bit and look at the systems overall again and evaluate chiller sequencing and system optimization methods. We're going to divide these further by system configuration, as that affects how our plants are controlled and optimized. We'll start with the chilled water side and then go to the condenser side, always mindful that chillers see the effects of both. Historically, there's been a progression in design, from constant flow to primary-secondary flow to variable primary flow. Some, especially existing chiller plants, have migrated to a combination that varies the flow through the chillers and the secondary loops at the same time. The configuration that you have determines which energy saving strategies are possible and suitable. Now, constant flow was common in the 1980s and earlier, and still works well for small chilled water systems, especially those with few coils and designed for the minimum chiller flow and highest DeltaT. Systems with multiple coils use 3-way valves to maintain constant flow throughout the system. It's a really simple system for the chiller, and because it has fewer components, the entire system can be easy to control, especially when there is only one chiller operating at any time. Systems may even be able to use fan speed discharge air temperature control instead of control valves in some instances. Constant flow systems are allowed by ASHRAE Standard 90.1 when the total chilled water pump energy is 10 horsepower or less, or if there are 3 or fewer control valves, or if the system is designed at the limits of the equipment, and one limit is chiller minimum flow. Even though the flow is constant, a VFD can be applied to the pump motor in lieu of a starter, so you don't have to trim the pump impeller, and you won't have the temptation to put on a triple duty valve, as you no longer have the need for a balancing valve at the outlet of the pump, doing nothing for you but wasting energy.
Constant flow is simple and can be used on systems up to about 200 tons, as long as the system pressure drop is fairly low and a wider DeltaT is applied. Now, using a VFD at a set speed allows the flow to be decreased or increased in the future if necessary. If the system were balanced by trimming the pump impeller, flow adjustments would not be easy. This technique makes more and more sense as the cost of VFDs drop.
For constant flow systems, it's critical that coils are optimally selected, since the flow cannot be used as a variable to optimize energy consumption. Going with the lowest constant flow you can get means selecting coils for high DeltaT. Some coils are more capable of this than others, but in virtually all applications there is an option to improve DeltaT. Other considerations in coil selection include avoiding moisture carryover, cost, size, air pressure drop, and cleanability. It is also possible to put coils in series, for example by splitting the latent loads from the sensible loads to increase DeltaT. We went over coil fundamentals in the last broadcast, so I encourage you to watch that one for more information.
Using lower flow, high DeltaT coil selections are particularly important for constant flow plants, but there are many advantages in variable flow plants too. The important thing to consider is the overall plant energy efficiency. Although you don't necessarily have to use colder water to get a higher DeltaT, it may be the best option in some cases. If the chiller is producing colder water, it will use more power, but in many applications, the overall energy used by the chiller plus pumps will be less. That's why many in the industry, including ASHRAE's Green Guide, recommend designing chilled water systems for lower flow rates or larger DeltaTs. We've listed several resources on low flow designs in the bibliography in your handouts. There's another advantage of a lower design flow rate in the design phase. It increases loop time if you don't downsize the pipes. Now, chillers have a minimum loop time. One way to calculate the loop time of your system is by dividing gallons by GPM. It's the amount of time it takes for the chiller to see the same water after it's been circulated. If you don't have a long enough loop time, the chiller controls would likely become unstable and the system would perform poorly or unreliably. The required loop time varies by manufacturer and by chiller type. We've seen requirements on chiller mechanical specifications anywhere from 1 to 5 minutes. If the system is small, the volume of water in the system is often too low, and you'll need to add volume. The easiest and most common way to do this is with a buffer tank on the inlet side of the pump. The other option is to reduce the flow rate, which has the same effect as extra volume on the loop time. How do you know how much loop volume you have? The chiller report will tell you how much water is in the chiller itself, then use this chart for the volume per length of a certain diameter pipe. As we showed in the 2004 program, the need for a buffer tank can be minimized or even eliminated by using a low flow design. Here's one example. A 50-ton single chiller constant flow system. Using a 10-degree DeltaT costs about $10 per ton of cooling and needs about 100 gallons of buffer tank for minimum loop time. The equivalent system with an 18-degree DeltaT uses a third of the cost for pumping and doesn't need a buffer tank.
That's all the design options we'll cover today for constant flow systems. Now let's move on to operation. Constant chilled water flow systems have fewer optimization opportunities than other configurations. Now that's not necessarily a bad thing. It helps to keep things simple. If you follow the advice of many and designed a high DeltaT system, you're well on your way to a high-performing chilled water system with very low pumping energy. But if you've used colder water to get your higher DeltaT, you may be concerned about the energy used by the chiller to make it that cold at part load conditions. One strategy commonly applied in constant flow systems is chilled water reset. Resetting the chilled water temperature set point upward at part load conditions can save 1 to 2% of the chiller energy per degree of reset. Most of today's chillers have the option for chilled water reset built right into the controller. You simply add an outside air or return water temperature sensor and enter a reset ratio. The amount of savings you can get changes based on the chiller type and whether or not it has a variable frequency drive. And let's not forget ASHRAE 90.1. This model energy efficiency standard has been inconsistent on chilled water reset. It was in, then it was out, and now it's back in the newly released 90.1 2013 mid-cycle supplement. The new version gives two alternatives, either pump pressure or chilled water reset, based on critical valve position. We'll compare these two options for variable flow systems. But for constant flow systems, chilled water reset is the most common control optimization because the pump energy is constant. We don't have additional pump energy to offset our chiller savings. This is not the case in variable flow systems, and we'll come back to this later. Now, the caveats. Chilled water reset, when used, should be dynamic and not a permanent override. With this strategy, too much of a good thing can drive your system off a cliff. That's because if low DeltaT syndrome is present, that is, the DeltaT is smaller than it should be given the load condition, chilled water reset can make the problem worse. Zone temperatures and/or valve position should be monitored, and the reset should be released when loads get too high for the warmer temperature water to effectively cool. Release or reset downward as coils and/or fan speed get to nearly wide open in one or more zones. And finally, chilled water reset gone awry shrinks the effective capacity of the chiller and should be removed when the chiller needs to be loaded further. The practical limitations of constant flow get more undesirable as the system gets bigger and has more chillers. The system creates and pumps cooling that is not used at part load conditions. As we've said before, if you're at chiller minimum flow all the time, it's just additional chiller energy. But most systems have pumping and chiller energy waste. The second limitation is when you have 2 or more chillers in parallel, if and when you operate the system with both chillers rather than just for redundancy. We talked about this in the 2004 and 2008 broadcasts. Dropping a chiller and a pump means your coils could be starved for flow. And if you leave flow through the chiller that's off, you don't meet the pump isolation requirements of the energy codes and standards. You mix chilled water and return water, and you waste energy. If you have a variable speed drive on the pump, you may be able to overpump the operating chiller, provided you stay within the limits of the chiller. And DeltaT is the only way to load the chillers. While we do expect lower DeltaT at part load, if it's due to a system problem, it may not track well with load. When this happens, you lose system cooling capacity. Release chilled water reset and look for your worst offending coils to improve system DeltaT. We'll come back to this in a few minutes. But for these reasons, primary-secondary systems became popular. These systems are also called decoupled systems. It has 1 or more chillers, typically in parallel, with at least as many pumps as chillers, a secondary side pump or pumps, and a bypass line that decouples the flow through the chillers from the flow through the air handlers or terminals. The secondary flow varies because there is no bypass at each coil. Instead, 2-way modulating valves open or close in response to load. The flow through the chillers is different than the flow through the building or process, and the surplus or deficit flow automatically flows through the decoupler bypass pipe. Here I'm showing a dedicated primary pump per chiller and different styles of chillers. The dedicated pump arrangement is typical and allows for the pump to be commissioned for the flow that is expected through its chiller. The primary pump is constant speed, while the building pump or secondary pump is variable speed. The appeal of this configuration is how it accommodates chillers of varying ages, flow rates, pressure drops, and capabilities. For this reason, it is relatively easy to expand the system. The system controls are forgiving and straightforward. Pump energy is reduced because the secondary pump energy falls with the cube of the load reduction. At part load, chillers are staged when the loads get high enough to require another chiller's flow. Circuit isolation is easy to accomplish. The chillers are happy and the coils are happy at a lot more loads. But this happiness comes at a price: more pumps, valves, electrical and pipes to connect them. The chillers never fully load because the chiller DeltaT is always reduced by the amount of surplus flow between the 2 sides of the system. Chiller sequencing is a flow decision in most cases. You stage a chiller on when you need more flow through the secondary side, and you stage off when the surplus flow is equivalent to the flow of the chiller you intend to turn off, plus a little bit extra so you don't have to turn it back on too soon. Now, the forgiveness of the controls means that energy waste is silent. Equipment and occupants are happy most of the time. So let's take a moment to discuss some of the other ways that primary-secondary systems have hidden energy waste and the benefits and likely outcomes of the things we attempt to do about it. There are 2 common problems that we see in primary-secondary systems. The bypass line is improperly designed, or additional chillers are turned on before the operating chillers ever get to full load. Now let's go through those and see how we can resolve them. We see this problem a lot. The decoupler pipe has so little pressure drop that the water short circuits, and the direction of the flow in the decoupler is not a reliable indicator of flow surplus or deficit. Both the add and subtract sequence are affected. So aim for the decoupler to be at least 10 pipe diameters of straight pipe long. If you can't do that, some of the less disruptive resolutions to the bad decoupler design include installing elbows in the decoupler to increase its pressure drop, installing a tank in the decoupler, or putting a check valve in it. the last one is not universally approved. Some people advocate the check valve in the decoupler to prevent deficit flow, while others disagree or are ambivalent about them. Now, the potential risk of this is that pumps will be in series, and this may or may not be a problem in your system. Now let's move on to another common hiccup. The chillers waste capacity, and in most systems are incapable of being fully loaded due to system effects. So let's explore the effect that the primary-secondary system has on chiller capacity. To illustrate, we need to put flows and temperatures on our system drawing. In this case, we have the secondary side calling for 750 GPM of 44-degree water. Since our chiller pumps are sized for 500 GPM per chiller, we have both chillers on for a combined total of 1,000 GPM. A quarter of that, 250 GPM, is not needed by our two-way valves in the system and returns directly to the chillers through the decoupler pipe. We can calculate the effect this surplus water has on the temperature of the water coming back to the chillers. So let's first assume that the coils are selected for a 10-degree DeltaT, and because there are only two-way valves in the system, we might therefore always expect 54 degrees to come back to the central plant. Using the water rule that flow coming into a T always has to flow out of the T, we have 250 GPM at 44 degrees, mixing with 750 GPM at 54 degrees, giving us 51.5 degrees entering each chiller. The chiller capacity is therefore fixed by the flow times the temperature difference. In this case, we have 500 times 7.5 degrees of chiller DeltaT divided by 24 for water, and that gives 156 tons each. Since the chillers at 10 degrees of DeltaT were 208 tons, that's a 75% capacity. So this system is working great. The chillers are at 75% load, and the load is also 75%. So what's the problem? Well, we all know that things don't always go as planned. For many reasons, we often don't see the designed DeltaT coming back from the loads. You may have heard of it with the medical-sounding name Low DeltaT Syndrome. Now, this is a coil and a hydronics problem that gets blamed on the chillers. One of my colleagues used to call it the case of the incredible shrinking chiller. So let's start sleuthing. For this one, we'll pick a spot in the sequence just before the second chiller has to come on. The same system now has the building demanding 480 GPM at 44 degrees. We are just nearly balanced, only 20 GPM in the decoupler pipe. Now suppose we only get a 9-degree DeltaT in the loads, when we expected 10. When you purchased that 208-ton chiller, you thought that's what you were getting. Nope. You really got a 500 GPM chiller. As in our last example, each chiller's capacity is fully defined by the flow times chiller DeltaT. As the return temperature falls, the chiller unloads to meet set point, and we just lost an extra 10% of the chiller capacity. In a little while, the second chiller will be staged on, and the surplus water will depress our chiller return water temperature even further. If you only get 90% of your design building DeltaT, you'll only get 90% of your installed chiller capacity. I've seen buildings designed for 10 degrees of DeltaT running at 5 or 6, so they only have 50 or 60% of the installed chiller capacity. Their operators are looking to buy another chiller when they should first figure out the reason for the low DeltaT. No matter how clean the floor is in your chiller plant, the performance of the chilled water loop will likely degrade at some point from its intended levels. Any component that allows cold supplied chilled water to escape to the return line without absorbing a full amount of heat steals from the system DeltaT. Now, these DeltaT criminals also go by the names three-way valve, but two-way valves can also fail to perform. Other reasons include valve leakage, poor calibration, or controls that panic and allow large volumes of water to chase a load that isn't really present. You might also see that valves close to the pump perform differently than pumps further out in the loop. Excess pump head prevents the valves from seating properly. Variable speed drives are ideal for preventing excess pump head. However, the pump may be programmed to stay at a higher pressure to keep one or more valves nearly wide open. That's where calibration and inaccurate control come in. If you have a valve that is constantly wide open because the control point it's using is either faulty or out of calibration, you may still see excess pressure even with variable speed pumps. And the final culprit is chilled water reset. By this I mean anything that makes the temperature supplied to the valve to be warmer than design. This could be due to deficit flow or a control optimization that's doing more harm than good. Getting to the bottom of the causes of your poor DeltaT is crucial, but it isn't glamorous work, so it's often avoided. So what can we do if we can't resolve all of the low DeltaT problems? Can we minimize its effects on our chilled water system? There are 3 effects: excess pump energy, loss of chiller capacity, and as a result, too many chillers online. One of the effects of low DeltaT is extra pump energy. So you're wasting energy on the primary and the secondary side in this system. One option is to reduce primary pump energy to right-size the operating chillers to meet the load, and therefore reduce surplus flow. This could include a swing chiller that's smaller than the others, or more smaller chillers, installed to more closely match load, and I mean flow, and limit the surplus flow in the bypass pipe. By putting a smaller chiller in the lineup, the controls will stage the smaller chiller on and off again before adding a larger chiller. This could also mean installing 3 chillers instead of 2. Another option is to preferentially load 1 or more of the chillers, with the remainder of the load handled by decoupled chillers, either in parallel or series with a preferentially loaded chiller. Now this means moving the decoupler pipe. One variation I've heard about is to use a load-based add sequence. This is essentially a variation on chilled water reset. The chiller is not added until the building load says that the loads are high enough to need it. With the flow imbalance, this then leads to deficit flow and warmer than generated water being circulated to the loads. We save primary pump energy and delay a chiller start, but the chillers are wasting energy, making the water colder than it will be circulated. Plus, with the warmer circulated water, we use more secondary pump energy. To reduce the number of chillers online, convert to variable primary flow. Put a variable speed drive on the chiller pump and change the water flow rate to meet the load. And then the least disruptive change is to keep the decoupler, but change to variable primary, variable secondary, and match primary and secondary flow. I'll discuss this in a few minutes. So this restores some of the missing chiller capacity, reduces the number of chillers operating, and the amount of surplus flow. However, it does not resolve low building DeltaT. Another way to deal with the chiller capacity loss is to release chilled water reset if it's active, or lower the chiller set point. This reduces the flow in the secondary loop and delays the need for adding a chiller. Most of the time, the chiller has the ability to make the water colder. It will come back at the same temperature or warmer than it did before, depending on the style of coils in your building. Some or all of the lost chiller capacity is restored. Now, while we're on the subject of chilled water reset and its potential for worsening low DeltaT syndrome, let's talk about its proper use now within a system with variable flow. Optimizing the primary-secondary system has 2 somewhat competing options: pump pressure reset and chilled water reset. Now, we've already talked about chilled water reset in constant flow systems. Now let's examine this compared to the other option in variable flow systems, including decoupled systems. Pump pressure reset results in slowing down the pump on the secondary side, either based on remote differential pressure or based on critical valve position. On systems with pumped coils, you might look at the highest pump speed. As the load falls and the fan speed turns down to a certain point, controls for the terminal or the air handler begin to close the chilled water valve. The pressure upstream of it goes up, and nearby valves see an increase in pressure too. In turn, they'll close if it results in overcooling. So valves are seeing lots of different pressures all the time. As an aside, this is one reason why there is a movement to install pressure-independent valves in variable flow systems, to keep the valves from having jittery control. A remote differential pressure sensor provides information about the average load downstream of its location. The control resets the pump pressure setting downwards until one valve or tertiary pump is nearly wide open, or to keep the remote differential pressure at set point. So how does chilled water reset compare to this, energy-wise, in a variable flow system? The challenge that we have in a variable flow system, in this case variable secondary flow, is that we now have a trade-off between reduced chiller energy and increased pump energy. Another challenge is that energy simulation software does not model the effects of water temperature on coil performance. Something like 1 to 2% per degree of reset is assumed, but that's just the effect on the chiller. What about when you include the secondary pump? Since the models are no good to us, we have to use a different method. Here's the brute force method, using chiller performance data and coil selections. For the base case, I assumed pump pressure optimization followed the affinity laws with some system losses. For the reset temperature alternative, I used 48 instead of 44 degrees, with two options for condensing temperature, 75 or 65. I calculated the required flow rate and pump energy at 75, 50, and 25% load. At 75% load, the coil I had selected couldn't take 48-degree water and still meet the load. The flow went above 100%. But before we spend any more effort on figuring just how warm we could allow the water to be at 75% load, let's see if the other load points encourage us. What we find is a great opportunity to increase system energy in the variable flow constant speed chiller regime, and a clear advantage to chilled water temperature reset in systems with variable speed chillers. If we were to generalize, we'd say that chilled water reset makes more sense to do first in constant flow systems, variable flow systems with a healthy design DeltaT, so they already have low flow, systems with variable speed chillers at low load conditions, variable primary flow systems where minimum flow is already achieved, and systems with waterside free cooling. As a secondary control strategy, consider chilled water reset when the flow is low enough that the chiller minimum flow bypass is being invoked. Turning the temperature up opens the valves and may avoid the need for some or all of the bypassed flow. And of course, we said it earlier, beware of permanent overrides. It is possible to have too much of a good thing. If there are some zones that just are never happy, they can defeat the logic of both strategies. Be vigilant and investigate valves that are always wide open. System differential pressure-based reset is less prone to rogue zones. The differential pressure signal will represent a more generalized view of how unloaded the building is.
So that was one instance where our chiller starter choice affected our optimization strategy. There are a few others. In one of our 2013 programs, we identified some improvements to full load sequencing when using variable speed chillers in plants with 3 or more chillers. We see there is some merit to bringing the additional variable speed chiller on sooner than full load, but not across the board. The savings can be considerable from doing advanced sequencing. I showed earlier the fraction of chillers shipping with drives today, but too much of a good thing is also possible here. A key consideration about variable speed chillers is minimum load. Variable speed chillers unload differently. That should not surprise anybody. As with any variable speed device, the important attribute is turn down. How much can we slow down? It's tempting for chiller manufacturers to put a really large variable speed compressor on a chiller and never run it at full speed. This gives better full load performance, but may result in odd performance at other load points, sometimes even resulting in the need for hot gas bypass, which wastes energy. You may or may not see this effect in the part load metric IPLV. Work with the manufacturer to make sure that the chiller unloads as you expect it to, both with and without condenser relief, with minimal use of energy-consuming hot gas bypass. And the final consideration we need to check is whether or not we're going to use backup power generation for the chillers. As one of our past newsletters identified, variable speed drives produce nonlinear electric loads and may require larger power generation equipment, not necessarily smaller. Consider this if you are using backup generators with variable speed chillers.
All right, let's move on to the next configuration, variable primary flow. Since the mid-1990s to early 2000s, variable primary flow systems have become quite popular. It was we chiller manufacturers who insisted on constant flow. Now that chillers have more sophisticated controls, we can allow varying the flow through them. In this system, we have at least one chiller, at least one pump, and a minimum flow bypass. Here you see a 2-chiller VPF system with 2 manifolded pumps and a minimum flow bypass sized for the minimum flow of the largest chiller. Modern chillers are capable of operating with variable flow without nuisance trips, provided the system controls are done properly. The most attractive benefit is that a new system costs less to install, 3 to 8% less, and it has 3 to 5% lower lifecycle cost. DeltaT to the chillers remains constant until minimum flow bypass is necessary. This allows the chillers to be fully loaded before additional chillers are staged on. Cooling energy is not pumped unnecessarily. The disadvantages of this system configuration include system controls complexity, older chiller capabilities, and how to accommodate varying sizes and vintages of chillers. So let's first talk about system control. When operating the variable flow system, the biggest difference is the chiller staging and component sequencing. We talked a bit earlier about the direction and amount of flow in the decoupler pipe driving the decision about adding and subtracting chillers in a decoupled system. In variable primary flow, we don't have a decoupler. We really only care about whether or not the operating chillers are able to meet set point. We have the pumps make enough flow to deliver the remote differential pressure. We add a chiller when the leaving temperature rises above set point for sufficiently long enough or high enough. Before subtracting a chiller, we predict if the remaining chillers will be unable to meet set point. Percent RLA is a useful indication of how loaded the operating chillers are. If we take away one, the remaining chillers can't go above 100% RLA. Now, if we manifolded our pumps together, not only are the pumps redundant, we may be able to run more pumps than chillers. The number of pumps to run is more or less independent of the number of chillers to run. In this system, we delay adding a chiller automatically, as the pumps are driven by the load and ramp up well past what would perhaps have been the design flow rate of the chiller. The minimum flow bypass opens whenever the flow across the chillers is below minimum. We can use a flow meter or a chiller differential water pressure to determine when this happens. As discussed in the 2008 program on small chilled water plants, staging on a second chiller is a difficult transition. The flow rate through the operating chiller is cut in half, and the chiller has to unload fast enough to avoid the low evaporator refrigerant cutout. Simply stated, some things have to happen quickly and some things slowly. The new circuit has to open slowly, and the chiller has to unload quickly. If they don't, the chiller will have a nuisance trip. Now, this stops being a nuisance pretty quickly and may become a deal breaker. Now, some chiller types and vintages are better at variable flow than others. Check with the chiller manufacturer to find out the limits. A 30% per minute rate of flow change is generally okay for most comfort cooling applications. You may have to upgrade chiller controls or the chiller for the system to be reliable and the operators and occupants comfortable when varying the flow through the chillers. Asymmetry is not your friend in the system, whether through deliberate swing chillers you inherited from a previous incarnation of the plant, or by system expansion with different styles or configurations of chiller heat exchangers. When pumps are manifolded, we mentioned the benefit of only staging on pumps when we need them for the load. If some chillers are smaller than others, or if they have different pressure drops, they will load unequally and unpredictably, and the controls can get quite complicated trying to account for it. Transitions are made that much harder. If the pressure drops are not too different, it may not be a deal breaker. Modern system controls can accommodate VPF, but manual plant control is difficult. A minimum flow bypass must be installed in most applications to keep the chillers online during low load periods when the system flow is below the chiller's minimum. Having said all that, we still see this as a popular configuration choice for new systems especially, because the first cost and operating costs are so attractive. We've been doing variable primary flow long enough now that we have seen a lot of people using it when it's not ideal. Small systems have challenges with VPF. I've been brought into projects doing variable flow when there is only 10% turn down before the chiller reaches minimum flow. and it may only have 1 or 2 air handlers. This is not a good application. I like to think that if a system is small enough to need a buffer tank, then the pump savings from VPF are pretty small. So then we're down to lower first cost, saving a pump. Constant flow systems have only 1 pump. If the low is already low, variable primary flow may not be the right way to go. We like to see at least 40% available system flow turned down before considering variable primary flow. This brings us to limitations of smaller, more packaged chillers. Unless the manufacturer has specifically designed it for variable flow, for example by having 3 pass options, you may end up with a variable flow system that has very little flow turned down. It's also more difficult on some chiller designs to select for a higher DeltaT. Brazed plate heat exchangers have performance degradations that can make more than 14 or 16 degree DeltaT impractical. Keep this in mind when optimizing the coil selection or reselection, or find a smaller chiller with a different style of heat exchanger. Another method is to put the chillers in series with each other, or with something like chilled water or ice storage.
Susanna brought up an interesting point. Should we pipe the chillers in parallel or in series? In a variable primary flow system, we're balancing a potential increase in pump energy with a reduction in chiller energy. Double-digit chiller energy savings are quite possible. A huge advantage of a series system in a variable primary configuration is control simplicity. The transition from 1 to 2 chillers and back can be seamless. We increase chiller flow to load our chillers. What we really want to know is how much of the time my series configuration will increase pump energy once the flow rate is variable. As we illustrated in detail in 2008, the minimum flow bypass also plays a role in keeping our parallel configuration online. So we must look at all the components of the pumping energy rather than looking specifically at the evaporator pressure drop. Because we don't have to bypass for minimum flow, pump flow of a series system is actually lower at most loads. Now, let's see the impact that has on the pump horsepower. On the left, we have the parallel chillers. Note that the green boxes identify the times when the pump horsepower is lower. Pressure drop through the chiller drops with the square of the flow rate. So, even with a higher initial system pressure drop through the evaporator, it evens out very quickly. That's right. Below roughly 70% of system load, the series chiller arrangement results in less pumping horsepower than the parallel chiller arrangement. For this example system, with smaller chillers and a high fraction of bypass flow. So do the math for yourself using your system to see if series can help lower your pump energy as well as your chiller energy.
But it's not for every system. When you put chillers in series that have staged compression, like with scroll compressors, the upstream and downstream circuits tend to fight each other. The upstream chiller makes set point minus a differential for long enough, turns off a compressor, and the downstream chiller sees that as a load increase and starts a compressor. Then the upstream chiller restarts a compressor and the downstream chiller shuts one off. Carefully setting up the chillers can minimize this interplay. Using ice storage gets us the benefits of series chillers and lower flow rates without having this problem. Now, there are certainly other advantages of thermal storage, as we discussed in depth in 2009. It's easy to preferentially load the upstream machine by giving it the same set point as the downstream machine. But to preferentially load the downstream machine, you must dynamically reset the upstream machine set point. The final configuration that is gaining in popularity is the variable primary, variable secondary. It's an option to consider when retrofitting existing decoupled plants and the chillers are new enough to tolerate a moderate amount of flow variation. 30% per minute is a good target. Converting to variable chiller flow within a decoupled system allows for the sequencing to accommodate chiller capacity, not chiller pump flow. Fewer changes need to be made, and they're much less invasive than if we were converting from decoupled to variable primary flow. For our example, we're going to start with primary pumps that are manifolded. First, the change involves adding a VSD to the primary pumps and opening the balancing portion of the triple duty valve wide open, using the VSD to balance the flow rate and set the maximum pump speed. You'll likely save energy just by doing that. Next, install temperature sensors in the return line from the system and to the chiller. Decoupled systems may have these already. Control the pump's VFDs so that the return temperature to the chillers is a degree or two lower than from the system. This ensures a little excess flow in the bypass line all the time, and more importantly, that the system chilled water set point is always maintained. Finally, install flow sensing devices such as DP sensors at each chiller to ensure minimum flow rate. If the temperature control of the pump VSD results in flow approaching the chiller's minimum, this sensor will speed up the drives on the pumps. Now let's turn our attention to the condenser or heat rejection side of the chilled water system. There are two main options, water-cooled and air-cooled. Here you see your basic water-cooled chiller plant. We have condenser pumps, valves, and cooling towers connected to the chiller's condensers. It's generally true that water-cooled systems are more energy efficient than air-cooled systems, especially when optimized in design. This is because they operate against the wet bulb temperature, which is lower than the dry bulb temperature that air-cooled chillers operate against. There also is a phase change, the latent heat of evaporation that is removed from the condensing circuit of a water-cooled system. But with the latest advancements in air-cooled chillers, we can't just design any old water-cooled system. We have to be smart. Let's review the objective and some guidelines that will help make the water-cooled system as energy efficient as it should be. We've devoted a lot of time to condenser side design and optimization in the 2011 and 2013 programs. Our objective is colder water from the cooling tower without having to pay a lot of extra energy or first cost for it. To do this, we select good towers with good flow turndown. We think 80 GPM per horsepower is achievable for tower selections, nearly twice the efficiency of the axial cooling tower minimum code requirement. For the range, that is, the difference between the entering and leaving water temperatures, 12 to 15 is appropriate. This equates to 2 to 2.5 GPM per chiller ton. This will affect the centrifugal chiller selection, so ideally the chiller is also new or being replaced. Approach gets a lot of attention. This is the difference between the leaving water temperature and the wet bulb temperature. Simply driving for a low approach temperature is not uniformly good across climates and building types. We wrote a newsletter on the topic for a deeper dive on this issue. And finally, flow turndown. If we have a good enough flow turndown, we can flow one chiller across two towers. That would be a 50% turndown, which is the minimum code requirement. Even better would be a 66% turndown, or 1/3 of the flow, so we could run one chiller across 3 towers. You may even be able to eliminate water flow control valves if you can always run all the towers. Flow turndown is accomplished with special nozzles, cups, or dams inside the tower to keep the tower fill uniformly wet. Now here are some takeaways from our 2011 Engineers Newsletter Live on upgrading existing chilled water plants. As Mike mentioned in the beginning of this program, variable speed drives are becoming commonplace on centrifugal chillers. But what about adding one to an existing centrifugal chiller? It benefits operation when there are enough operating hours at low lift conditions, for example, when the tower water temperature can be reduced. If the chiller is to be replaced, compare 2 chillers with the same price, one with a variable speed drive and the other with more heat exchange surface and therefore premium efficiency. Perform an analysis with both demand and consumption costs. You can use the new MyPLV tool to calculate and compare annualized performance with your building type and climate with different chillers from any manufacturer. Cooling tower fans are often a great retrofit application for VFDs. From a chilled water pump standpoint, there is low-hanging fruit for applying VSDs, especially in constant flow systems that have flow or typical DeltaTs and high flow rates. But what about the condenser water pump? Shall we put a drive on that? As we discussed in the 2011 and 2013 programs, you need to determine whether or not dynamically changing the condenser water flow rate should even be considered. If you've already minimized the condenser water pump kW, for example by reducing design flow rate to 1.5 or 2 GPM per ton, it may not even make sense to take the time to look further. The pumps already have a really low contribution to the chiller plant energy picture. If you already have VFDs on your cooling tower, reducing the tower fan speed dynamically can achieve a lot of the potential savings, and it's simpler. But if you do decide to reduce flow, there are limits to consider, including the minimum chiller condenser water flow rate, not only from the chiller's perspective, but also from the tower's and the pump's perspectives. As you examine combinations of load and flow rate, you'll need to identify limits that keep the chiller out of surge. Documenting the sequence of operation and assisting with the commissioning of the system should be required of anyone dynamically modifying the condenser flow rate. So let's review the savings we can expect from varying the speed of the various components in the system. Shown here is our base system configuration for the office building in Chicago. The building has an air side economizer, so during many hours of building operation, the chill water plant will be off. Note the design condenser water flow rate of 3 GPM per ton is something we'll reconsider, as are the chiller type and the cooling tower set point. Since we often see building operators use a fixed set point, our base reflects that. There are many variations in the system to consider when discussing optimizing the water-cooled condensing system. Each component could have a variable speed drive. Based on our earlier trends, code requirements, and practicality, I'm going to assume that all components have drives on them. This leaves us with design and control options for the condenser system. Now, the original designer gets to pick the condenser water flow rate. What if it were lower, say 2 GPM per ton? This probably means a different chiller selection if the chiller is centrifugal, and if the designer and the controls company must work together to optimize the sequence. That's true whether it's just tower set point optimization or a combination of condenser water pump and tower controls. To help us decide which design and control strategy to use, we'll calculate the annual energy efficiency for the system in terms of kilowatt hours per ton hours. By canceling the hours, we simplify the term to annualized kW per ton for the entire chilled water system. The base case is a constant speed chiller, single speed tower fan, condenser water design flow rate of 3 GPM per ton, a constant speed condenser water pump per chiller, and a tower controlled to maintain 85 degrees. We analyzed performance with 1, 2, or 3 chillers. The annualized kW per ton was drastically reduced with more chillers, but the difference from 1 to 2 was significantly greater than from 2 to 3. This makes sense since the chillers themselves will likely operate in a more efficient mode, and ancillary energy consumed by constant speed equipment is much higher for 1 large chiller than it would be for 3 smaller chillers. Our next alternative only optimizes the cooling tower set point. We see that this reduces the annualized kW per ton about 0.1 in all cases. The next alternative begins with the base case, but applies a variable speed fan to the cooling tower. Just putting a VFD on the cooling tower fan reduced energy consumption more than applying optimal control to a fixed speed tower fan. We can see why 90.1 required tower fan speed control back in 1999. Now we'll take the same system and optimize the cooling tower fan control. Again, there is a significant savings simply by dynamically finding the optimal tower set point. Now some people might stop here, but there still is some low-hanging fruit to be picked. The trends are going toward variable speed because it's so tempting to just put drives on everything and assume they'll do the trick. But that simply turns up the heat on our controls to deliver the highest system performance. System design and control are critical for applying variable speed components properly and not wasting the investment. Our base case uses a fixed 85-degree tower set point. This happens more often than most people believe because the system was commissioned with the design day in mind and to make sure the chillers are capable of working on the hottest day of the year. But on all those other days, we can optimize our cooling tower fan control and use the drive to slow down the tower fans. Note the huge change from improper tower fan control, no matter how many chillers we have. What if we change the condenser design water flow rate? Since we're interested in the highest system performance, when we reduced the condenser water flow rate, we left the pipe sizes the same and used the same cooling tower fan. Reducing the water flow rate reduces condenser water pump power and energy and gives us a better, closer cooling tower approach temperature. The towers are more effective when given warmer water. The lower flow rate provides very good savings for fewer chillers, but as the number of chillers increases, the performance benefits are less significant. This lines up with the industry's understanding of flow rates and is true for all chiller manufacturers. Taylor described the same results in an article published in the December 2011 ASHRAE Journal. In that analysis, he reduced pipe sizes, which also reduced some of the possible condenser water pump energy savings. So his lowest life cycle cost was derived from a combination of lower first costs and lower operating costs. Now let's vary the speed of the condenser water pumps of a system using the older 3 GPM per ton design flow rate. This could be a retrofit scenario reusing existing chillers. Now there are some savings due to proper control of the VSD, but the system performance is very similar to a system designed with reduced, constant condenser water flow. The final option is to keep with the lower condenser water flow rate and optimize the condenser water pump control. Reduce the flow further when possible. As expected, the system performance improved, but only a little bit. Reducing the condenser design flow rate, but not varying the flow, achieves high performance without increasing control complexity. The design team can choose a lower flow rate and simpler controls, or a higher flow rate and increased complexity. The results are similar. On existing plants, you might not have both options. If you aren't able to get a new chiller, one that's capable of low flow and a slightly elevated condensing temperature, you must control variably to low flow, but only some of the time. There is one final caveat. A suboptimal condenser water flow design requires optimized control to achieve best efficiency levels. If the control were removed at some point, for some reason, the efficiency of a variable flow condenser system regresses to become worse than low flow, high DeltaT constant flow. Let's summarize all of the conclusions for the condenser side of the system. Multiple chillers improve system efficiency. Optimally controlled variable speed tower fans save a lot of energy, and that control is absolutely critical if variable speed chillers are applied. Proper designed condenser water flow rate is important and allows simpler condenser water control. Variable speed condenser water pump control can save some energy, but primarily on over-designed systems. After looking at other building types and locations, the conclusions seem to hold true, except variable condenser water flow may not save energy in very hot and humid climates. And we do have some concerns that the controls may be modified or turned off at some point in the life of the plant, so the savings are less certain for variable condenser flow systems than for low flow optimized constant flow condenser water systems. So that was complicated. Is there any way to make it easier? Enter air-cooled chillers. Here you see the major components of an air-cooled chiller with compressor, condenser fans, and condenser coils. There's seemingly less to discuss here as the chiller itself does its own optimization, and there is far less for the system designer to do. However, there have been some recent advancements implied in this product class that make sense to discuss. This may be the age of the air-cooled chiller. That's because air-cooled condensers don't use water. This is not a trivial consideration. Air-cooled systems can be easier to maintain, however, they typically don't last as long as water-cooled systems do. Air-cooled systems don't carry water treatment costs and the chemicals because the chilled water system is a closed system, unlike the condenser water system. Now let's talk about efficiency. The minimum code for new air-cooled chillers is 50% more efficient than it was just 5 years ago. An air-cooled chiller with a variable speed compressor, variable primary flow, and variable speed condenser fans is tough to beat. As in water-cooled, we have a split in 2013, introducing Path A and Path B for air-cooled chillers. We see that minimum chiller full load efficiency remains flat, but there are more efficient chillers that can be selected. The dots represent data from premium efficiency chillers, one selected for very high full load and part load performance. What does this tell us? There remains additional chiller efficiency levels to design into chiller plants. In fact, over 25% higher full load and 45% higher part load efficiency. And this is even more significant because the performance levels don't rely on higher level control optimizations. Most of the optimizations for the all variable speed air-cooled chiller system are inside the chiller controller itself, as standard from the factory. Let's discuss 4 trends in today's air-cooled chiller systems: heat exchangers, variable speed, sound attenuation, and chillers as heaters. In heat exchanger design, there is a move toward all aluminum designs, including microchannel technology. The benefit of this is there is less copper to aluminum interaction and a lower required refrigerant charge. Variable speed condenser fans improve system efficiency and sound. And variable speed compressors give more efficiency improvements. Finally, the change to refrigerant 410A created more superheat, the amount of heat you can withdraw from the refrigerant gas at a given pressure before it begins to condense. Not all air-cooled chillers use 410A. Another option is to use dual condensers or reversible refrigeration circuits to make the chillers become air source heat pumps. This is a lot more common in Europe. Optimizations for air-cooled chillers rely on balancing condenser fan speed with discharge pressure. It's really the same as water-cooled, but with one less heat exchanger, no condenser water pump, and done by the chiller controller. The chiller part load performance data shows the benefits of both variable speed condenser fans and staged and/or variable speed compressors. Another optimization for air-cooled chillers is thermal storage. In our 2009 broadcast, we showed how air-cooled performance changes proportionately more than water-cooled performance, because there is more reduction in the outdoor air dry bulb temperature than in the wet bulb temperature. So we see a bigger benefit from running the air-cooled chiller at night than during the day. If your building doesn't have load at night, this means storing the energy at night to deploy during the peak times of the day. We've shown you some MyPLV examples in other programs. The tool works equally well for air-cooled chiller systems. Here you can see the performance of some of the new air-cooled chillers within the context of a whole year's operation. It's great for figuring out how long it will take for the more expensive, advanced air-cooled chiller to pay back through lower energy costs. Here's a summary of that initial report. Payback years range from 1.3 years in Miami, where there are a lot of hours of cooling, to as high as 3.7 years in Quebec, where there are fewer operating hours. I encourage you to play with this powerful analysis tool when specifying or purchasing your next chiller, whether air or water-cooled. Inevitably, comparisons are to be made. Is water or air-cooled better from an energy standpoint? What about from a total cost of ownership standpoint, including maintenance, water costs, and equipment longevity? Are there other attributes of the two styles of condensers that change this answer? What about climate, first cost?
All good questions. And we have excellent tools like Trace for doing these types of comparisons for your building type, in your climate, with your business objectives. Let's review some takeaways from the presentation today. Mike, why don't you start us with what you feel are the chiller-related trends?
Efficiency is and will continue to be a common theme in any trend discussion. Through design and careful analysis of equipment choices, engineers have the ability to design not only highly efficient chiller plants, but also high-performing buildings. Interestingly enough, manufacturers are not at max tech yet, but are challenged as we draw nearer to that point. As we saw with ASHRAE 90.1 2013 minimum efficiencies for chillers, there is still room to significantly exceed stated minimum efficiencies. Now, one of the challenges manufacturers face as they drive towards max tech is compressor design. We learned impeller design and therefore compressor design is driven by an application's conditions as defined by lift and desired tonnage. Something many may have not known was that refrigerant choice is another significant input to compressor design, driving choices downstream. The result? Select chillers based on how efficiently they handle the prescribed lift and tonnage requirements, not on their bearing sets. Also, since refrigerant is one of those critical design inputs, we need to pay attention to the global shift towards next-generation refrigerants. So, what can you do? Simple. Continue to do what you have always done. Seek the most efficient solution for your project and also properly contain and manage the refrigerant in your system. Ask manufacturers what their plans are for the future. Understand impacts to efficiency, capacity, and flammability. know that there are exciting things happening in the world of refrigerants, and they bring benefits. And of course, as we mentioned in the beginning, all the planning and design work is for naught unless the system is controlled appropriately. As controls continue to get more and more sophisticated, we see protocols opening up with BACnet leading the way. Finally, controls allow for more than just simple on-off capabilities. They also can provide vast amounts of data, helping us to better understand real-time our system's health. Diagnostic and prognostic abilities continue to grow and help us better understand this data. Anticipating problems before they happen will help avoid downtime and allow us to optimize systems, ensuring they run at peak efficiency, and customers realizing the energy savings they expected when they purchased their equipment. Susanna covered the power of lowering the flow rates, whether all the time when the flow is constant or some of the time in the case of variable flow systems. For controls optimizations, chilled water reset can be a powerful optimization tool when done in the right application and not too much, and it's the only game in town for constant flow systems. In variable flow systems, even with a system design with a 10-degree DeltaT, high flow, chiller speed capabilities may change your optimization. Chilled water reset may be more appropriate to do first with variable speed chillers, assuming they have good compressor speed turndown available. Pump pressure reset is first for constant speed chillers. In both cases, watch the critical valve to make sure it's not always wide open and defeating the logic. Now, summarizing the condenser side of the system. Chiller tower set point optimization is very important, especially if the tower and chiller are variable speed. Again, for new systems, there's a great benefit lowering the flow rates, whether all the time when the flow is constant or some of the time in the case of variable condenser flow systems. For existing systems with high design flow rates, like 3 GPM per ton, dynamically varying the condenser flow allows for some of the condenser system energy savings without requiring a new chiller. Air-cooled condensers, especially when packaged as air-cooled chillers, simplify things a lot. Advancements in compressor, heat exchanger, variable speed components, and controls have made air-cooled chillers more efficient and quieter in recent years.
As always, there are a number of publications available that provide more information on the material covered today. We mentioned quite a few, and a bibliography detailing these resources is included in your handout. Additionally, all programs are available on DVD at trane.com/ENL. All are accredited for continuing education, and many are available on demand free of charge. So visit trane.com/continuing education for a complete list to satisfy credentialing requirements. Many are LEED specific. And please remember to fill out a survey and let us know what you think of today's program. AIA members, remember to turn in your member information to your local site coordinator. Now, as I mentioned earlier, we do read the evaluations and we listen. And based on your feedback, in 2016, we'll start out by providing insight into getting the performance out of airside economizers. We'll give you an update on new fan efficiency regulations and the latest advances in fan technology. And we'll present a do-it-yourself program on modeling chiller plant performance. And finally, we'll host another acoustics-related program, Designing for Outdoor Applications. So ask your local host for event details. Thanks for your time today. We look forward to seeing you next year.